Okay, so it's astrophotography without a telescope. Let's get going. First of all, let's talk about the basic equipment you need, and I bet you can all guess what the first one is. A camera, obviously, but it would be perhaps a DSLR, a compact, or even a smartphone you can use to do astrophotography. I'll be talking about that later on. So you can use just about any camera you can lay your hands on. Ideally, you'd have a remote shutter control or use shutter delay so that you don't have to shake the camera when you're taking a shot. And also a tripod is essential. But that's it, a regular sort of camera with shutter control and a tripod, and you can start doing astrophotography. The camera types, I want to just talk about this. I wasn't expecting such experienced people only to be present tonight, but nevertheless, I think it's worth just going over this quickly. I'm going to talk about the DSLR first of all, the digital single lens reflex camera, which basically has all of these components. So the light from the scene you're trying to photograph comes into the lens system. There's a mirror here which reflects that light up to a pentaprism. The light then reflects round that. The eyepiece lens is there, and that's where you look. So you see the scene that you're focused on. When you press the shutter, the mirror flips out of the way. The light from the scene you're photographing falls onto the image sensor, and then the image is saved from the sensor to a memory card. So you're probably all aware of that, but that's the way the single lens reflex camera works. You can also get digital single lens cameras that are mirrorless. So let's just remind ourselves how those work. Again, you've got your lens system here in the camera. The light from the scene falls onto the sensor, and when you fire the shutter, then the data from the sensor goes to an electronic viewfinder, which is just another sensor really, and you can look at that. So that's what you see. You don't look all the way through the lens as you did with the single lens, with the mirrored camera. And then, of course, the image is saved to the memory card. So those are the two types of DSLR cameras that we use. The focal length of a camera lens is worth just talking a little bit about. Focal length of a single lens is defined quite simply. If you have parallel light coming into a straightforward single lens, then that light will be focused to a point. And the distance between the lens and that point, that's the focal length of the lens. Now, unfortunately, modern cameras are a lot more complicated than that. So instead of a single lens, you have a whole array of lenses which are all there to remove various artifacts and make corrections to the various lenses and so on and so forth. So it's more complicated than this single arrangement, but nevertheless, that whole bundle of lenses can be sort of treated as a single lens. The parallel light comes in, it brings it to a focus, and there's your sensor, and so this is the focal length then. Okay. I want to just mention F number. Again, I'm sure you're all aware of this, but let's just go through it. F number is the focal length divided by the aperture. And so for a 50mm focal length lens, if the aperture is 3, then you get f16. So aperture 3 means you've got a very small opening, a very large f number. So large f number means small aperture, and so on. At 12, you've got f4, and so on and so forth. So very small f number is associated with a very large aperture. And as the aperture increases, then the field of view and the amount of light on the sensor increases. We are always talking about ISO. Let's just try and get it reasonably clear in our minds what it means. You'd think it would stand for something electronic. It doesn't actually. It stands for the International Organization for Standardization. I was quite surprised when I learned that. I was expecting something electronic or optical. It is a measure of the sensitivity of the image sensor. So higher numbers means that your sensor becomes more sensitive to light, which allows you to use your camera at night. But a higher ISO, greater sensitivity, as I mentioned, this results in more noise. So you've got a rather grainy image. It's rather like having listening to the radio, and you suddenly turn the volume right up and the sound will start getting distorted. It's the same sort of effect that you're getting here with a higher ISO, greater sensitivity. So what you need to do when you're taking your pictures is experiment. You want to try and balance the sensitivity of the sensor, which will cut down the time you need to expose, but also balance that with how grainy the image might be. And the only way you can get that sorted is to take several pictures with different settings until you get the sort of picture that you want. Now, which lens is best to use? And of course, it depends on what it is you're imaging. So for example, if you're trying to image a planet, a small image, or if you're trying to image the Milky Way, a huge image, then it'll require different lens arrangement. But generally, you'd want, for a fairly wide angle view, something around f.25, something around 20 millimeters focal length. Sometimes you'll get a zoom lens supplied with the camera when you buy it, and it's generally 18 to 55 millimeters as a typical lens system that will come along with your digital camera. And that's quite a good range. So anything with a very much longer focal length, I'm going to regard as a telescope. And so I'm going to concentrate very much on the sort of camera, by and large, that you might take on holiday with you. This, if you want to take a notice of this, it's a bit difficult, but if we're recording this, then we'll probably have it available to you on the website. But there's a really good article, Camera Lenses for Astrophotography by Jerry Longus. And that's really worth looking at, gives you a lot of information. Also, I'd recommend getting the Photo Pills app. It's really good. It's got tons of information in it. It's got a system in it where you can work out where the Milky Way is and how best to photograph it. It'll tell you where the planets are at any one time, and it's full of loads of information. It's really worthwhile getting hold of Photo Pills, and it's free. Now then, focus. It's probably the most important bit. If you get the focusing wrong, then it screws up everything. And I'm sure, as you're all fairly experienced astrophotographers, I bet you've all spent at least 1 or 2 nights collecting loads and loads of data, only to find out when you look at it, your focus wasn't spot on and you've wasted the whole night. So getting the focus right is absolutely crucial, and you really have to spend some time making sure you've got that as best as you can. You can do it using manual focus to set the focus on a distant object. If the moon is out, it's great to set your focus on the moon, especially if it's a partial moon and you can get the sharp point of the moon, and that's really good to set the focus, if not a very distant object. Or you can use autofocus on a nice bright star, and then as soon as it's got its focus fixed, switch over to manual focus, and that'll hold the focus where you want it to be. Just a word about that. A lot of people think that you can get the focus right by setting your camera at infinity. Well, that doesn't actually work. You have to come a little bit back from infinity, you'll discover, if you follow this procedure. So that's important, get that right. And again, always test it. Once you think you've got it right, take some photographs and have a look at it. And if it's not right, then adjust it again. It's really worth taking a lot of time to get the focus right. Now, what about camera settings? There's a rule of 500, or some people call it a rule of 600, which is something that you need to use to avoid distortion due to the Earth's rotation. Obviously, the Earth rotating means your camera's rotating, so if you've got a fairly long exposure, all of the stars and objects will be trailing. Instead of nice round stars, you get things that look like a sausage. So the longest exposure then is calculated by 500 or 600 divided by the lens focal length in millimeters. And this is a rule that most people use, and it works very well. So for example, if you've got a 20mm lens on your camera, then your longest exposure will be 25 seconds if you're going by the 500 rule, or 30 if you're following the 600 rule, but somewhere between 25 and 30 is as long as you should leave your camera exposure. And of course, if that doesn't give you sufficient intensity of the object you're looking at, then of course you'll do what we normally do in astrophotography. You'll take a whole series of images so that they can be summed. The ISO, which is, I said, is sort of like the gain, would generally recommend between 1800 and 1600. But again, it's something you can experiment with. And then post-processing, I always use Photoshop, but there are other programs around that you can use. So, but Photoshop or Lightroom work well. And there are plenty of guides on the internet about how to use Photoshop and Lightroom to process your images. All of the cameras that you purchase have an infrared filter in them. And the reason it has that is because the sensors are particularly sensitive to the red end of the spectrum. And you don't really want that. You want the sensor to look at the scene the same way your eyes look at the scene. So what they do is they put a filter in that takes out some of the infrared and near red light to give you a more realistic picture. So for example, here's a picture taken with a camera with the filter in, and it looks exactly as you'd see it with your eye. But if you take the filter out, then it looks like that. And you think, well, why say that? Just leave the filter in. But in fact, that red color, the infrared and the red end of the spectrum, is really what you want to see as astrophotographers, because it's the wavelength of light that comes from hydrogen. It's the alpha hydrogen emission that's lovely and red, and nearly all of the objects in the sky that you would want to try and photograph are going to have some element of hydrogen alpha, red color in it. So it's difficult, this, because if you do have your camera adapted and the filter taken out, you can't then put it back in again. So you end up with a camera that's dedicated to astrophotography. But I just put that in to show you. Here's another picture. Here it is with the infrared filter in. You can recognize it as the Orion Nebula. And with the filter taken out, you see how much more of the hydrogen emission that you capture in the image. That's a decision you'd have to make. If you want to use a camera without a telescope and you want to use it dedicated to astrophotography, it's worth considering having the filter removed. So we're nearly at the end of the talk. I told Adrian this is a very short talk, but I'm hoping we'll have some discussion at the end. But let's have a look at some example images that you can obtain just with a simple camera and no telescope. Some of these are Adrian's. Here's a beautiful shot of the moon, and you can see the Earth shine on the surface of the moon. And down below, he's kindly indicated what the settings were. He's got a 200mm focal length lens, ISO around 800, and a 3-second exposure, f6.3. So you're getting a beautiful image of the moon. Here's an image I might have shown you before. This is an image from my bedroom window when the aurora were around. And again, it's ISO 1600. And for the lens I was using, 20 seconds. You can see the stars are all nice and sharp. And there's the color of the aurora. Here's another one. Very unstable, I'm afraid. I was standing on the back of a boat hand-holding a camera, so that's not so good. But nevertheless, the aurora are there. And this was taken with a small compact camera, the sort of thing you can just hold in one hand. Very simple. The Lumix T71. Don't know if you know it, but it's just a small compact. Ian Glendinning, Noctilucent Clouds, another lovely photograph. I particularly like it because it's got this lovely foreground of the sheep in it in silhouette, so it makes a very beautiful picture. Unfortunately, he seems to have had a dust particle or something on his sensor, but apart from that, Noctilucent Clouds, beautiful. Here's another one by Adrian. Got a lot of stuff in here. We've got the Orion constellation, which you can see. You can even see the nebula down here in the sword. And he's even captured a meteor. So that was a great night. You don't know what sort of meteor that was. Can you remember, Adrian? Probably not. Was it the which shower that might have come from?
It was March, so it was probably just a random meteor.
Just a random.
I just got lucky.
Yeah.
Lucky.
But you can also see the Pleiades up here. So, you know, this is just a straightforward camera, and you can really do quite interesting and beautiful astrophotography. Here's the details. Nikon 120mm, ISO 800, 2-second exposure. And as Adrian says down here, if you want to capture meteor shower, then you need really to do lots and lots of exposures.
I suspect that should say 20-second.
Oh yes, 20-second. Okay, would have been good if it was 2 seconds. Okay. Now, rather than restricting your exposure time to stop the Earth's rotation, what you can do is buy a device that will track your camera with the Earth's rotation, very much like you have on your big telescopes. But you can get small ones that will just take your camera. So here's the Ioptron device, which is a nice compact tracker, and your camera sits on the top like that, and you line it up through this little scope here. You line it up with the pole star, and then as Earth rotates, your camera rotates with it. And then, of course, you can extend your exposure times for as long as you like, which is a big advantage. So here is one I took. Again, we're looking at the same scene. We're looking at Orion, and we're looking at the Pleiades. It's 30 seconds tracked, but look, the stars are all beautifully sharp, and you get a nice picture, and you could have had the exposure as long as you like, almost. Okay. Here's another one tracked, Comet Neowise, and again, look at the lovely sharp stars, and there's the comet that visited us last year. And then, of course, there's the Milky Way. Everybody likes to photograph the Milky Way. It's really good. This is tracked as well, 30 seconds track, and you can get, you know, a really beautiful picture. If you go a little further afield, like a lot of our members did, was it last year, went to Namibia, and a group of you, and Kathy managed to capture this picture of the Milky Way. Isn't that beautiful? Really lovely photograph she got there. So I was very envious of that. I've never ever managed to get the Milky Way that good. Must have been really clear sky. You were there, weren't you, David? Yeah? Yeah, very good. And then there's time-lapse photography. This is where you take a photograph and then you wait a bit and you take another shot and then another shot and another shot, and it builds up, overlaying all of the movement of the stars into a single image. So you get the effect of the Earth's rotation, and of course you get star trails showing where the stars have been during the time of the exposures. And you'd need time-lapse control, so you want a control that triggers the camera at certain intervals, around 20-second exposures, ISO as always around 1800, 1600, about between 2 or 10 seconds intervals, so at least the Earth's had a time to rotate a little bit. And you might take 50 or 100 exposures. You just set it going and wait till it's finished. And you experiment, as I'm always saying. Have a go, have a look at what you've got, and then adjust things until you get the sort of picture you want. There's a free software called StarSax, which will add all of the exposures together for you. You can look for that, but there are other ways which I'll touch on in a moment. Or you can even use all of the different shots you've got to make a time-lapse video. I'll show you an example of that at the end. The GoPro camera has a setting for doing time-lapse at night photographs. It's already set in the camera's software. So the little GoPro camera, which has an extremely wide field of view, is really great at taking star trail pictures. There's one that was taken with the GoPro and pointing obviously at the pole star, and that's my back garden. But there's a really nice example of star trailing done with something simple, just a GoPro camera. You can also do the same thing with a smartphone. If you fix up the smartphone on the top of your tripod, I made this bit of wood to do it and a couple of clamps just to hold the phone in place, then you can use your smartphone to take these sorts of pictures. If you use a piece of software which you can get from the Apple Store, it's called Nightcap, and it's really good. It has all of this control for the iPhone. It's got advice, plenty of information. It deals with ISO for you, and it has timer, it has an interval programmer, the whole load of stuff, and it will sort out star trails for you automatically. All you have to do is press the button and it does it. So if you do have an iPhone, look up Nightcap app. It's really, I think it's free, and it's great. Here's an image taken with my iPhone. Again, I've no idea what these lines were. I don't think they're meteors. That's a bit too strong, but I don't quite know what that was. But anyway, you can use that software with an iPhone to do reasonable astrophotography. Now, I told you that you could, if you take a lot of time-lapse pictures, you could stick them all together to make a video. You may have seen this before, but let's see what happens. Watch for the meteors. Yeah. There's another one and another. And that's it. So there you are.